Okay. Good afternoon, everyone. Welcome to my PhD dissertation defense. My name is Tongduan Li. I'm working with Dr. John Bosch in the Adaptive Signal Processing and Information Theory Research Group. And I'm also working with Dr. Stephen Weber in the Model and Analysis of Network Lab. The title of my dissertation is on multi-source, multi-sync hyper-edge networks, which includes three topics: enumeration, region computation, and hierarchy. So first, motivation. It is shown that in an information flow network, coding may outperform routing, where the coding means intermediate nodes are allowed to mix the input packets, while the routing means the nodes simple to receive and forward. There exists a basic relationship in the network, the automatable source rates versus the channel capacities on the links. So similarly, in a storage system, it is also shown that coding can outperform the simple replication, and the basic relationship there here is the automatable source file sizes versus the hard disk capacities. It turns out that these two types of problems can be generalized to a multi-source, multi-sync hyperedge network, where the hyperedge captures the property that nodes are allowed to transmit same information to the different nodes. We are trying to calculate the rate region of this type of networks, where the rate region here is the relationships between source rates and the edge capacities, as the inequality shown below the figure. So it is an open problem to get the rate region in general, especially manually. So that's why we are interested in using a computer to calculate the rate region. For the convenience of this presentation, I introduce the notation here. We denote the network size as a k-EU pair, which means there are k sources and EU intermediate edges. And basically, we made three major contributions on this topic. So first, we teach a computer to calculate the rate region and give automatic proofs. Conventionally, when a network is given, a researcher has to sit at the table with pieces of paper and information inequalities and then try to derive the rate region by hand. It may take hours or days to solve it, or it is not solvable at all. Now, with our computational tool, one can easily through thousands or millions of networks in the computer to solve them in seconds or minutes. So having this powerful tool at hand, so we would like to see how many problems it can solve. That's why we made our second contribution. So we enumerate all networks for a given size. Again, it is almost impossible for a human to list all networks due to the large number of instances. But with our enumeration algorithm, it is easy to enumerate millions, billions, or even trillions general networks. So after we have so many networks, and we can throw them into our computational tool and get their rate regions, then the third problem comes out. So with millions or trillions rate regions, what to do with them? So it takes a long time for a human to read and remember all of them. So we have to learn something from them. Our third contribution is to build a hierarchy between these networks so that we can relate the network structures and rate regions with some important properties preserved in the relationship, such as the sufficiency of linear codes. In addition, we can construct new networks in scale that are solvable, given the solved smaller networks. So I will basically cover the three contributions into this presentation, but with a slight change of the order. So I will first talk about the enumeration and then talk about the calculation of the rate region for each of them. At last, I will define the network operators that build the hierarchy. So let's first look at the enumeration. And before talking about enumeration, so we should first have a look at the model. So in our model, there are k independent sources. Each has a source rate, and the output is a function of the source variable. Without loss of generality, we assume the output of each source node is the source variable itself. And each intermediate edge has a capacity constraint, RE. And for each intermediate node, the output variables are functions of the input variables. So the conditional entropy is 0 here. And for each sink node, it has access to some edges and demands a subset of sources. And the demands beta t here can be different for different sinks. And this general network model includes several special networks. One of them is the independent distributed source coding problem, shorted as IDSC. As it shows here, the left-hand side is a typical representation of IDSC, where sources are assumed to be available to all encoders, and each decoder demands a subset of sources. So as we can see here, it can be converted to our model. All sources are connected to one node, and 3 hyperedges come out. So the multi-level diversity coding systems, which was talked about in our previous general summation, are actually special IDSC problems, where the sources are prioritized. So like Y1 has a higher priority means that the decoder must decode Y1 before it can decode Y2. Another special network is the index coding problem. So here we can see there are 3 sources in the index coding problem, and all of them are available to one center node, which broadcasts the coded message to all sinks. There is only one bottleneck edge, and the sinks may have direct access to some sources as said information. So as it stands, it is actually a 3-1 hyperedge multi-source network coding problem in our model. Okay, now we have introduced the network model. For enumeration, we do not want to enumerate networks with redundancies, so we define a notion of minimality. As this example shows, though S3 is transmitting Y3 into the network, no sink is demanding it. So S3 is totally redundant and should be removed. And actually we defined 14 minimality constraints, but I'm not going to talk about them one by one. Instead, I will just show some examples. So here is another example for node minimality. As we can see here, G1 and G2 have exactly the same input, so they can be merged as one node. And similarly, for 2 parallel edges, where the parallel means they come from the same node and are connected with the same nodes as well. So these 2 edges should be merged as one. For sink minimality, this example shows that T1 has access to U1 and demands Y2. T2 has access to U1 and U2 and demands both Y1 and Y2. So since the decoding ability of Y2 is implied by T1 already, so we should remove Y2 from the demand list of T2. This condition is necessary because otherwise the 2 networks shown here, the left and the right, will be labeled as different, but essentially they are the same. Okay, now after introducing the minimality, another issue we should pay attention to in the enumeration is the equivalent networks, because we don't want to enumerate networks that are equivalent to each other, so that the rate region can be derived from one another. And as the example shown here, network 1 and 2 are essentially the same, because they have the same structure and just permuting or relabeling the source and edges. However, we can see that network 1 and 3 are not equivalent because the sources are only permitted at the source side, and network 2 and 3 are not equivalent because the sources are only permitted at the sink node. So so we would like to formalize the network equivalence class using group actions. And first, we would like to introduce the representation of a network. A network is represented as an ordered pair of Q and W. Each is a collection of ordered pairs again that I will define soon. So we label the sources as 1 to K and the edges as K plus 1 to K plus EU. And then the Q is a collection of IA pairs where I is from the K plus 1 to K plus EU, representing the edges. And A is a subset of the other edges and the sources. So basically Q encodes the topology of the network except the sink nodes. As shown in this example, edge 3 is a function of 1, 2. So we have a 3, 1, 2 here. Similarly, 4 is a function of 1, 3. So we have 4, 1, 3 here. Then W encodes the think demands. It says which source can be decoded by which edge. For example, here, 2 is decoded by 3, 1 is decoded by 3 and 4, and 2 is decoded by 4. So we have the W collection here. So since same source can be decoded by different things, we allow repetition of I in W, but not in Q, because we cannot redefine a edge. Now, having the representation, we can have group actions. So the group is the symmetry group of sources times the symmetry group of edges. So here the symmetry group actually means permutations. Since we cannot permute sources with edges, so that's why it is a direct product of these two groups. For an element in the group acting on a ordered pair, it simply permutes the elements in the pair. So further, for a network QW, so we simply permute the element. It permutes the elements in Q and W simultaneously. So two networks are said equivalent if there exists a permutation so that one can be obtained from another with under this permutation. So as this example shows, the two networks are isomorphic because one can be obtained by permuting source 1 and 2 in both Q and W from the other one. So if we consider all elements in the group, we can get all equivalent networks. That is the orbit. Orbit is a word in group theory, we just borrowed. So all networks in an orbit are isomorphic or equivalent to each other. Thus, in the enumeration, we only need one representative for each equivalent class. Actually, we pick the canonical one, where the canonical is defined as follows. So we sort the I, A pair using the lexicographical order, and then sort the QW and pick the minimum one. As this example shows, there are 4 isomorphic instances in the orbit. Here are the QW representations for each instance. The first one is the canonical one, because we can see the 3, 1, 2 is less than 3, 1, 4 and 3, 2, 4. And then next, the 4, 1, 3 is less than 4, 2, 3. So that's why the first one is the minimum. And we can also see why did we choose this edge representation? Why don't we simply use the node representation? Okay, firstly, by using edge representation, several minimality constraints can be easily taken care of. So for example, the parallel edge, we simply require no repetition of I in the IA pair, in the IA representation in Q. Also, we don't need to worry about the redundant nodes, since we don't use the node representation, and we simply treat the edges with the same input as outgoing edges of the same node. And another benefit is that another benefit by using this type of representation is that we have less orbit size in most of the cases. For example, we just showed, so there are only 4 isomorphisms in edge representation because we only need to consider the permutation of 2 sources and 2 edges. While in node representation, as shown here, you have to consider permutation of 2 sources and 5 nodes. So 5 factorial is 120. So there are in total 240 isomorphisms in node representation. Okay, having introduced the network model, minimality, and network equivalent classes, we are ready to introduce the enumeration algorithm. Our enumeration is based on the Letterspiel algorithm, which computes orbits of size j subsets pjx of a set x, incrementally in j. So as the picture shows here, so suppose we know the orbits on size j-1 subset. Letterspiel directly extends to orbits on size J subsets. In addition, it can have some test function f inherited, as long as the function f has the inherited property. That is, if a superset satisfies f, its subset will also satisfy. So for lattice view, the input includes the set X, group G, and the test function f, if any. And the output will be the orbits of the subsets of different sizes until you stop the process, either a fixed J or other stop conditions. Okay, so given the lattice view, we would like to enumerate all K, E non-isomorphic networks. So recall that our representation of networks is ordered pair Q and W. So we will first call lattice view to list all possible Qs. And the set X for lattice view is all possible edges, I, A, and the group is the symmetry group of sources times the symmetry group of edges. With some minimality constraints inherited, we call lattice view so that it defines the edges from 1 to EU. Then we define all the edges and stop. Now for each possible Q in the enumerated list from last slide, so we would like to configure its all possible things, W. We will call lattice view again. So here the W is Q dependent. So set Y for the lattice view is then the I, A pairs, where I is a source, A is a subset of edges and sources. In addition, there must exist a path from I to at least one edge in A, because otherwise there's no hope to decode I out. And the acting group is the same, so the two symmetry groups, the product of the two symmetry groups. We also have some minimality constraints can be inherited. And then we call lattice view again to list all W's. It first adds one thing, then second, and so on. Since the number of things are not fixed for a specific Q, and we stop at the point where there is no possible new things to be added on. Then for each obtained W, we test the other minimality constraints on the QW pair. So if it passes, we obtain a non-isomorphic network instance. So here is a summary of enumeration of networks with different sizes. So first row shows network sizes. Second row shows non-isomorphic ones. Third row shows isomorphic ones with edge isomorphism. And the fourth row shows isomorphic ones with node isomorphisms. As we can see, without isomorphism, there are already millions of networks. And if with isomorphism, especially node isomorphism, there will be trillions of networks. So with so many networks enumerated, for each of them, we can use our computational tool to get its little region, or at least the bounds on it. So next, I will briefly talk about the computation method, since I have covered it in my proposal. So recall that the root region is a relationship between source entropies and edge capacities. It contains all possible rates and source entropy vectors, satisfying all network constraints. It can be expressed using this formula, so which is an extension of the formula in Yan Yang Zhang Chuanzai 2012 paper. The difference is we modify the L4 constraint, the edge capacity, a little bit so that the edge capacities are variables now, and we can directly get root region expressions, while in their paper, the edge capacity are constants. As it shows, this formula involves the gamma n star here, and as you know, the region of entropic vectors, which is a 2 to the n-1 dimensional cone, and containing all valid entropy vectors. It is known that not all points in the Euclidean space are entropic, since not all points have associated distribution to make it a valid entropic vector. And we know gamma n star is not fully characterized yet for n greater than or equal to 4. It contains some nonlinear part, so that we cannot directly use the formula in last slide to get the root region. So the trick we used is to replace it with its polyhedral out and inner bounds to get a out and inner bound on the read region. So if the out and inner bounds match, and we obtain the exact region. In that case, the calculation becomes a general polyhedral computation problem. So we have an initial polyhedra, we add some constraints, and then do the projection. And the outer bound we typically use is the Shannon outer bound, and the inner bounds we used from representable matroids, including scalar and vector bounds. And I will not talk about these bounds because they are covered in my proposal. But I will talk about the notion of sufficiency here. So as the figure shows, if the scalar or vector bound match with exact read region, it is denoted as sufficient. Otherwise, it is called insufficient. But with the theta and the theta vector bound, and it may become sufficient at some point. And we will see later in the results here. So here is a summary of the read region results on different networks. The second column shows the number of non-isomorphic network instances, and the following columns show the number of instances that the associated inner bound can match with the Shannon outer bound, and thus exact read regions can be obtained. The inner bounds become theta and theta from left to right. As we can see, we can close the gap for more and more networks with the theta and theta inner bounds. So in addition, we can get the sufficiency of codes for some networks. For example, all 1-2 networks are scalar binary sufficient. All 1-3 networks are vector binary sufficient with just one more extra bit to allocate to the variables. Similarly, all 2-2 networks are vector sufficient with 4 more bits, and all 3-1 networks are vector sufficient with 2 more bits. And these are still under calculation. Okay. So as I said before, after obtaining so many read regions, we would like to learn from them. So next we will introduce the network operators to relate networks and construct new networks. So let's first see the embedding operations and their results on forbidden network minors. So as I said at the beginning, we would like to see if there exists some inheritance property regarding the sufficiency of a class of linear codes. So this was motivated from graphs and matroids. So in graph theory, we know that for all minor closed graphs, there exists finite number of minors. Similarly, in matroid theory, root of the conjecture size, there exists finite number of forbidden minors for linear representability. Like this picture shows, when a smaller matroid is not FQ representable, its extensions will also not be FQ representable. So it should be forbidden in a larger matroid as a minor. So we would like to see if networks have similar property. In that case, we may have a list of forbidden network minors for sufficiency of linear codes over a field. And we actually define 3 operations to obtain the embedded networks. So our first operation is the source deletion. As the picture shows, so when the source key is deleted, it stops sending information to the network. It is equivalent to say, okay, I set the source entropy HYK to be 0. And the things requiring YK will no longer demand it. The second operation is the edge deletion. So similarly, when edge E is deleted, there's nothing on edge E. So it is equivalent to set the capacity LE to be 0. The third operation is edge contraction. So in graphs, we know when an edge is contracted, the 2 nodes will be merged. But in networks, it is equivalent to say the input to the tail node will be directly available to the head nodes. Right? And also it is equivalent to say the edge capacity on this edge E is infinity. So it can send whatever available to the head nodes. And for each operation, we have the root-region relationship, which gives the preservation property. Here I just give one example for the source deletion. So while the other ones have a similar characterization. As I said before, when a source is deleted, it is equivalent to set HYK equal to 0. So the root region of the smaller one is simply the root region of the larger one, intersecting with HYK equal to 0, and then project out the YK, as demonstrated in the picture. So after considering all embedding operations, we can build a forbidden manner relationship between networks that a class of codes do not suffice. For instance, in our previous journal submission, for the more than 7,000 MDCS networks, there are more than 5,000 networks that scalar binary codes do not suffice. But there are only 12 forbidden manners among them. So similar results can be obtained for general networks. Though there are many new forbidden manners, as we can see here, for sufficient of scalar binary codes, we can still have some forbidden manner relationship among them. As it shows here, more than 37,000 insufficient 3-2 networks have one of them smaller forbidden manners as a manner, either by deletion or by contraction. And similarly, for the 2-3 insufficient networks, we also have the same relationship. So they have a manner of embedded in for these more than 60,000 insufficient cases. Okay, so after showing the embedding operations, remember we have another goal. As I said at the beginning, we have operators to construct the new solvable networks. So next, I will introduce the combination operators so that we can construct larger networks from smaller ones. And our first operation is source merge. As it shows here, when two sources from two different networks are merged, the merged source will serve as a common source to the two subnetworks. Our second combination operation is the sync merge. So when two sinks from two networks are merged, we simply union their input and requests, which will be the input and the requests for the merged sync. So similarly, as a sync merge, we have a intermediate node merge. When two intermediate nodes in the two networks are merged, we union their input and output respectively. Our fourth combination operation is edge merge. So when two hyperedges from two networks are merged, we create one extra node and 4 associated edges so that the upper two edges can replace the red edge here, and the lower two edges can replace the black edge here. So it is equivalent to create the two relay nodes on the two edges here, and then merge the two relay nodes. So it becomes the equivalent graph here. So for the combination operations, we also have root-region relationships between smaller networks and the combined network. So here I just give the source merge as a demonstration. When a subset of sources in network A1 is merged with a associated subset of the sources in A2, the root-region for the combined network will be the direct product of RA1 and RA2, and then forcing the source entropies of the pairs of sources in the merge to be equal. So as it shows here. And essentially, so we can simply replace the source variables in one network with the associated source variable in another network, as long as they are merged each other. Okay, and after considering all combination operations, so we can easily derive root-region for a big network from smaller ones. So here is an example to show that so the big network here cannot be directly handled by our computational tool since there are too many variables. But actually it is the combinations of the following 5 smaller networks which can be easily known, which we can easily know their root regions. Then we can obtain the root region for the bigger one as shown right here. by the combinations and use the rate-region relationships through the combinations. Okay, so we just showed that combinations can give us new solvable networks, but the question is, are these sufficient? The answer is no. As the picture shows here, by combination only, we may reach a portion of large networks. However, if we use embedding operations as well, we may come down to some new portion of networks, and then we can go up again to reach more networks. So we can play with both types of operations. Since one can apply combinations as many times as possible, there are infinite number of new networks. So to better quantize the number and do some analysis, we may want to set a cap to limit the size of networks involved in the combination process, as it shows here. So if the networks go beyond the cap, we will not consider them for the combination. Then we can define a notion of a partial closure of networks. So as the flowchart showed here, we start with a seed list of networks. We consider their combinations and manners, of course within the cap. So if there are new networks obtained, we add to the seed list again and do the next round of combinations and manners. And we stop when there's no new networks. So in this case, we can start from a tiny list and get many new networks. So as a demonstration, we start with we start with the 6 tiny networks. So which includes the single 1-1 network, single 2-1 network, and the 4-1-2 networks. And we set different caps and consider combinations only and or both. So the table shows the new networks generated from these 6 tiny networks and with different sizes. So first we see that with the only 6 tiny networks, we can generate more than 11,000 new networks with a not so big cap. Then we see that with the increase of the cap, the number of new networks increases even for smaller networks. So as shown here, 2, 3, and 3, 4, the number increases with the increase of the cap size. And we can also see that the embedding operations are really important in the process. As we can see, we obtain much more new networks by allowing embedding operations. So like from 16 to 155, and this is from 568 to more than 11,000. So roughly 20 times larger. So to further clearly see why embedding operations are important in the process, we give an example. So still take the 6 tiny networks as an example. Here the cap is 3, 4. As it shows here, with combination only, we can only get 3 2-2 networks. And we also give the sources to generate these. So as I show here, source merge of these two, source merge of these two, and node merge of these two. So we can only get 3. However, if embedding operations is integrated in the process, so we can get another 2-2 network. So as is shown here, and we start with 2 different passes, and then do so we first do some combinations, and then do some embeddings, and then do some combinations again, and then do some embeddings again, and to get this 2-2 network. So actually, and the rate region can be naturally derived through the paths. So actually there are 12 new 2-2 networks we can find by this way, using this cap. So this is just one example. And by going up and down, we can reach more networks. Again, this is just for the 6 tiny networks. And we even haven't included the a little more than 300 2-2 networks yet. So this is really just the starting point for this research, and we've already seen the power of both combination and embedding operations. Okay, so here is a summary of what we have done so far. We enumerated about the meanings of non-isomorphic networks and calculated their exact regions or bounds. Then we developed some combination operators and embedding operators to relate their structures and with regions to have forbidden manners for sufficiency of a class of linear codes. In addition, by using both operators, new solvable networks in scale can be constructed. So ideally, we would like to have a user-friendly interface for people to use our tool so that the users can draw or input a network. And our software will do the minimality check and also the isomorphism test, and then check if it is in the database. If yes, direct output the answer. If no, we can check if it can be handled directly. If yes, we calculate the reach region. If no, we will try to see if it is reachable by our operators. If yes, we can obtain the reach region through the construction. Otherwise, we may not be able to solve it right now. So for future research, we would like to propose some intriguing questions. So regarding the reach region problems, we would like to see when Shannon outer bound is tight, do they share any common structures? Each sub-question could be if Shannon outer bound is tight for all MDCS or IDSC problems. Another question would be is the number of forbidden manners regarding the sufficiency of a class of linear codes finite? Though we have built the relationships between forbidden manners, we haven't proven if the number will be finite or not, like the graphs and the matroids. Regarding the operators, we would like to investigate the coverage of the operators in all problems. Also, some more operators can be developed, such as the node and edge merge, and source and sink merge. So another question is we still don't have a notion of forbidden manner which can harness both operations, though we have the notion of forbidden manner capturing embedding operations already, but we don't have a forbidden manner notion for both operators. So that's also a very interesting problem to look at. Okay, here is a list of my publications during my PhD study. Not all of them are included in this talk, but you are welcome to have a look if you are interested in. So here are some selected references, and thank you for your attention. I would like to take your questions next. Thank you.